When you first open up the ViaWizard, you should be able to generate a ready-to-solve HFSS project by simply clicking on the Generate Project button. HFSS will be called behind the scenes and a single via will be created. As we can see by performing a validation check, the project is ready to solve. If you are looking to see some quick start examples, you may go to the External File Read button, and in the installation directory under Examples, there are many different via types that you can peruse to see if there's any that match your current design. By clicking on a file, we automatically load up the settings for this type of via. For instance, for a blind via, we're going to have the barrel radius be 0 on the layers in which we don't want to have a drill. And all of these are again ready to solve just by simply clicking on the Generate Project button. If you're interested in seeing the Help menu, you can see that just by clicking the question mark and clicking on the Open Help Document tab. I'd now like to talk about the different tabs that you see up top and the general flow of creating a via design. In the Stack Up tab, here we define all of the layers of your PCB. And by default, we're always going to have metal, dielectric, metal, dielectric. We can add layers and delete them with these buttons in the upper right corner. This first column is fixed, in which we're always toggling between metal and dielectric. In the second column, we can choose the different material types for each of the layers. For the metal, we have some common conductors, and for the dielectric, we can create our own materials and add them to this list. In order to add a different dielectric material, we can go over here to the substrate editor, add material, and put in the different dielectric properties here. And what we're doing is we're actually generating a frequency-dependent material model in HFSS. We're using the Georgiev-Sarkar model, in which will allow for a causal extrapolation of the loss tangent and the dielectric permittivity to higher and lower frequencies. And now after we've added this material here, we can now see in the pull-down menu we have access to that. The third column for thickness is exactly what it appears to be, in which we can control the thickness for both the metal and dielectric layers. On the fourth column, we have plane or signal as choices. For each layer that has a plane, we're going to draw a solid metal plane there. And on the signal layers, we're not going to draw a plane. So that would be reserved for creating pads or drawing your traces to escape the vias. Using the Pad Stack tab, we can define the via dimensions on each of the different layers. You see that the first column, layers, will have a single entry for each one of the layers that was previously defined in the Stack Up. For barrel radius, we're defining the outside dimension of the via, going through each of the different layers. Under pad radius, we are defining what the dimensions of the individual pads will be. So you can have varying dimensions of the pad for each of the individual layers. If we do not want to have a pad, we set this pad radius equal to the barrel radius. And so in essence, we're removing the non-functional pads in this case. The antipad radius and width and antipad height are linked together. This defines the clearance in any of the planes if a layer is defined as a plane. It's ignored if it's just a signal layer. If you define the antipad height to be 0, we're going to assume that we have circular antipads, and this dimension defines the radius. If we define both, then we're assuming that this is going to be the width and the height of a rectangular antipad. One other thing I should note here is one useful thing with these columns is that we can drag and drop the columns to do multiple edits of that column. So if we click on one cell and drag it down to the bottom and then hit return, we can do the multiple edits. These last two columns, AnyPad X offset and AnyPad Y offset, control the registration. And basically that's going to change the centering of this AnyPad around the barrel center. For the pad stacks, we can add as many ones as we want. The default is we have one signal via and one ground via. For a ground via, basically we want this via to attach itself to each of the different planes that have been defined. And for that we define the AnyPad radius to be 0. This means we're making an electrical connection and shorting these planes together. If we want to add an additional pad stack, we can simply do add, and when we choose that, we can change the dimensions of that via on any of these different layers. Using the Via tab, we can control exactly where we want to place our vias. By default, we have just a single via defined. If we want to add more, we can simply click the Add button and delete to remove them. In this case, if we want 2 of them, we can just add 2 and select the pad stack that we want for each of them. Using the pull-down menu, we can access the pad stacks that we previously defined. In this case, if I want a signal via and also a ground via, we can choose one of each. It's always important to have a return path in your design. It's not a good idea to try to simulate just a signal via in isolation, because we're not really accurately characterizing the return path that it would see if it was on a PCB. Typically there's going to be a ground via nearby or some other via or some other way of making the transition, so it's usually a good idea to also define a ground via in your project. These next 2 columns that we have here define the X and Y locations when looking at a top-down view of the vias. And if I want to put these on a 40 mil pitch, I can just simply add the Y dimensions for the second via, and we can see the top-down view. It's also important to note that when we're defining these ports, the traces in and trace out, they're going to be done in the X direction. So we want to make sure that we have a clear path in the X direction. Here we define the ports. We can use a pull-down menu. And for the signal via, if we want to have a trace come in and a trace go out, we can choose that first option. And for the ground via, we typically don't want to excite that, so we're going to use none. The trace layer in defines which layer we're bringing the trace in, and the trace layer out is going to be where it's escaping. And you may notice that there's only 1 in 4 as choices. We're listing only the layers that are signal layers, not the planes. We can define the trace width in and the trace width out. And if you have multiple vias, multiple signal vias that is, we can define a differential pair as well. If I wanted to explore some of the different options for the ports, I can add a via here and look at the pull-down menu. We've already been over none and trace in and trace out. With the coax launch top, what we're doing is we're taking a short section of coax feed and bringing that down to the top of the via. There's a small pin that presses into the center of the barrel, and the outside coax sheath is going to act as the return path. For the coax launch, we also have a trace going out. So in this case, we're launching from the top, and then we have a trace going on an out layer. For trace in, none out, what we're doing is we're providing a trace in, but leaving the none out for the user to draw the trace. This is useful if the user wants to define their own trace to escape, if you have a complex via array. Trace out, none in is self-explanatory. With the coax launch bottom, we're just bringing that coax feed in from the bottom and then providing a trace out. For the coax launch top and bottom, we're again providing a coax launch, but not placing a trace to escape so the user can define it. With the ground launch, what we're doing there is we're using the PEC sheet to short that via with the outside sheath of the coax. So this is only used if there's a coax feed provided. If there's no coax, this is essentially the same as none, in which there is no ports used for excitation. And finally, with the coax in and coax out, what we're doing is we're providing a feed on both ends of the via. And this is useful if you just want to look at the barrel-to-barrel coupling of different vias with no launches. There's no traces coming into that via. So let's say we wanted to also create a differential pair for this via. And if these two are the differential pairs, we can first provide a port for it and then define it as a differential pair, which we select which via we're pairing it with. So in this case, we're going to pair vias 1 and 3, the two signal vias. And by defining it as a differential pair, what we're doing is we're going to create a dog bone antipad, a clearance between these two vias, as well as pair the traces coming in. So the traces will come in coupled, and then they'll fan out to each of the different signal vias. If we do identified differential vias, what we're going to do is we're going to color code which vias are paired with one another. And if we want to delete any of these vias, we need to make sure that they're all single-ended and then hit delete. And what that's going to do is just simply delete the last via in the array. The last tab, Options, is not necessary for setting up a via project, but is often helpful for tweaking some of the parameters used by HFSS. The first section we have here is General Options, in which we can control the units to be different lengths of measurement. We can check the box to automatically run HFSS, so whenever we click Generate Project, it's automatically going to launch HFSS. Otherwise, we're just going to create a text file that can be later read into HFSS. If we also check the Solve project, we're going to launch HFSS and also launch the simulation so it starts solving. Under Model Options, we can control the number of facets that we use. Ordinarily, everything is a true surface in which we have perfect circles, but we can also facet that, in which we can reduce the accuracy slightly, but it also makes it run quicker and mesh quicker. Under Model Resolution, we can control the minimum dimension that we care about. And for de-embedding, what we're doing here is we're automatically removing a section of trace that we use to launch the via. So the traces coming in and the traces going out are automatically taken out of the simulation results. We could also set that to none, in which we do include the traces, or specified, in which we de-embed a certain length. The backdrilling parameter, when set to a non-zero value, will automatically remove a section of the via from the bottom of the board. So if you're testing out the backdrilling depth on your vias, you can set this to a non-zero value, and then a parameter rule will be added to the HFSS project, in which this backdrill will automatically be stripped out of the bottom of the via. Etch back percentage controls the amount of etching done on the traces that are going in and out of the via. This is removing a percentage of metal based on the thickness of that plane. So if you have a 1.2 mil thickness on your layer and you set etch back percentage to 100%, we're going to remove 0.6 mils from either side of the top part of the trace, forming a trapezoid for that trace. Including dog bone will create that clearance between differential vias. But if you have differential vias that have individual antipads without that dog bone clearance, you can uncheck that box. Block dielectric will create a single dielectric block for your project. If you check that, we're just going to take the first dielectric material that is seen in the stack up and apply that to all of your layers. So we're just going to create a single block of dielectric with the metal inside. When this is unchecked, we're going to create individual layers of dielectric in which you can change the material properties of each of them. Under solve options, we first can choose whether or not we want to use an interpolating sweep or a discrete sweep. We can also control the start and stop frequencies by explicitly entering the frequency in Hertz, or we could specify a rise time in which we can automatically compute the stop frequency based on the rise time. Here we're just using the knee frequency of 0.35 divided by the rise time. We can control our frequency step as well as the delta S and the max passes used by the adaptive mesh. And these buttons over here, we've already seen that when you click Generate Project, what we're going to do is we're going to launch HFSS and bring in the geometry. But we can also store and read the VIA project as we've defined it. So with all of these different dimensions that we've already entered here, when we do store, we can store these as a text file to be used later. So now let's take a look at the actual HFSS project that's generated. And you can see that we have our two vias defined. One of them has the trace coming in and the trace going out, as well as a ground via next to it. And if we zoom in, we can see that the ground via is indeed connected to the planes, while the signal via has the antipad defined. We can see, if we expand the solids, that we have our airbox automatically defined, our copper vias and planes, and the dielectric. So we created 3 dielectrics for each of the different layers. And each of these were made using the frequency-dependent materials that we specified using the wizard. We can also expand further, and we can see that for each one of these objects we have access to the full history. So if we wanted to go in there and tweak some of these variables, we have the variables that control the different things such as the dimensions of the plane thickness, or we could double click on the different properties and manually change them ourselves without actually going through the variables. And all of these variables are accessible either by clicking on the high level HFSS project, in which we can see some of the important variables, or by going through HFSS design properties. There's many more variables defined, many of which are hidden, which we can control such things such as the overall dimensions of the HFSS project, the thicknesses of all of the individual layers, and things like the registration. You can see that the ports and boundaries are also defined. We use wave ports. And the de-embedding distance has been specified. You can see here the blue arrow specifies the de-embedding distance, and what that is doing is it's actually going out to the edge of the antipad. So we're de-embedding this length of trace all the way out to the edge of the antipad where this cross-section is no longer uniform. For the boundary conditions, we're simply applying a radiation boundary to that external airbox. For the analysis, we're specifying the solution frequency that we defined using the rise time. Here it is 10 gigahertz. The maximum number of passes and the delta S were also defined. By default, we're using first order with the iterative solver. Then under that setup, we also have our interpolating sweep, which we're going out to the maximum frequency that was defined by the setup, and we're using the step size that we specified using the wizard. If we want to set up a parametric analysis, we can do that by going into design properties and choosing which variable we want to optimize. So let's say we want to change the pitch. We could go in here and go to optimization and include that as one of the variables. So now if we were to go in there, we can try changing this variable. You can see that everything shifts with changing that dimension. We're moving the ports, the trace, everything associated with that. So if we want to set up a parametric analysis, we can right-click under Optometrics and do Add Parametric. So if we click on Add, we can go down there to that ViaWizard3 and we'll start it at -10, go up to 10 mils, and we'll do a step of, say, 2 mils. And we'll see our sweep definition here and the table of the different parametric variations. If we want to visualize what that looks like, we can click on that via, right-click, and do View Animate. And this doesn't really matter much here, but we'll choose VIA1 for the animation, and we can look at the VIA1_Y and enter in the same dimensions that we did before. And here we can see the total sweep that we're looking at. Another thing I'd like to point out is the over-etching that we talked about previously, which if you look at this trace, you can see that it's not a perfect rectangle like you might assume. So we actually have a trapezoidal shape in which that top length of the trapezoid is equal to the bottom length minus 100% of the thickness of the layer. So that etchback percentage controls how much we're going to reduce that top dimension. And that, you can see here, is controlled by the different variables in the HFSS project. Another important variable that we defined in the wizard was the backdrilling parameter, and which we can see here under VIA1 backdrill. In this case, it's a completely through via, which we're transitioning from the top layer to the bottom layer, so it doesn't really make much sense. But if we set that to a positive number, and see what we're going to do is we're going to bore out that bottom of that via. We're essentially going to drill it out, and obviously here we're destroying the functionality of the via, but if you were to have a via that was making a transition on the inner layers and you wanted to remove some of that stub, you can experiment with this variable to see how that affects your via performance and what depth you need to control your back drilling to. And the final thing that I like to point out is, again, over here with the question mark. So if you have any questions or comments or enhancement requests, please feel free to email myself or Tony Denisi at the email addresses you have here.